great pleasure to welcome all our viewers back to the videos of Crystal Clear Electronics. Today's presenter is Ambrus Zelei.
Thank you, Zalán. My partner in the presentation will be Zalán Gyuricza. The first video on control and regulation showed us that we use so-called control loops when we want to control a process. For example, to keep an electric motor at 1000 rotations per minute or to set the arm of a robot to a certain height. To do this, you need a reference signal. It is what we want to keep, for example, 1000 rotations per minute. We also need an open or a closed loop controller that decides how the actuator should change the process, for example by applying more or less voltage to the electric motor.
You've said that it's either an open loop controller or a closed loop controller that makes the decisions. Can you tell me the difference between the two?
In short, the difference is that when you use closed loop control, you use some kind of measurement to check whether the intervention moves the process you want to control in the right direction. With open loop control, there is no such thing. We are confident that we can predict the effect of the actuator, so there is no backchecking.
The open loop control therefore seems to be a little simpler. So let's start with this.
So, let's start with the definition of open loop control. A control scheme is called open loop control if the reference signal is fed into the controller, which forms the control signal, which then operates the actuator, which ultimately affects the process. It's very important that the controller does not know the impact of its intervention.
To this, we say that the loop is open.
Exactly. There is no so-called feedback and no sensor at the end of the process. It also means that we need to know in advance how the controlled process will respond to a given control signal. For example, I know that I need to apply 12 volts if I want 1000 rotations per minute on the motor shaft and 6 volts if I only want 500. Now, these were just random numbers, of course, but in this way, you need to know your system and you need a model. It's very important to note that the interference from different sources can also affect the process, for example by changing the load on the engine. If we don't know these in advance, we won't be able to avoid their effects. And this, among other things, will make it necessary to use closed loop control. But for now, let's stick to open loop control. Let's look at the block diagram. You can see the main building blocks of open loop control in orange.
I think it would be best if we went through them one by one.
Yes. At the beginning of the block diagram, we give the reference signal to a variable speed electric drill. We want to set the speed of the drill bit to 1000 RPM by adjusting the speed control of the drill to 1000 RPM. Behind the speed control adjuster, there is probably a potentiometer which gives an output signal to the rest of the elements in the block diagram. The reference signal conditioning can be that the limits of the potentiometer represent a safe range of possible RPM values, which prevents you from setting an arbitrary value.
So it won't let me run the drill at too high speed, right?
Exactly. And then, the safely conditioned reference signal is used by the controller. The controller could be, for example, an algorithm running on a microcontroller that uses the reference signal to generate a signal that corresponds to 1000 revolutions of the motor using data stored in memory. The point is, therefore, to know in advance what signal the controller needs to generate for a given RPM. The actuator is a power electronics circuit that can drive the motor. In a store-bought drill, the controller and the actuator are more of a fused power electronic circuit without a microcontroller, and it's scaled so that the controller produces the voltage to the actuator so that the idle speed of the chuck is 1000, but if you start drilling a solid material, you'll feel and hear the speed start to drop. What does that indicate?
That it is obviously an open loop control, so there is no feedback.
Exactly.
So then it's an external interface. So let's talk a little bit about external disturbances using the drill as an example.
Yes, let's move on to the external disturbance. The value that we have set is probably valid when the drill is being used under load. If we turn it on at idle, that is without load, the chuck speed will be a bit higher than the set value. If we use the drill improperly, like holding the chuck down by hand as strongly as we can, this can mean a disturbance signal that the controller cannot compensate for, as the effect was not known beforehand. More precisely, the drill manufacturer did not know this in advance. Since it was not known, the control logic won't request a higher torque from the actuator, and the speed most certainly won't be 1000 RPM, but will go slightly lower or the drill will even stop. Let's see. You can hear clearly that the speed is dropping. I can't stop it by hand, but you have heard that the speed has fallen a lot.
It has become much slower.
We can hear it by the sound. Generally speaking, open-loop controlled devices are simpler because they do not contain sensors, just as the drill didn't detect the output speed, so it is not required to select or embed them into the system or to interface their signals to the control equipment. Moreover, an open-loop control logic can be simpler than a complex and fast closed-loop system.
Therefore, open-loop control in general is simpler than regulation. So why do we still need regulation in some cases? I think it is time to go into this in more detail.
In contrast to open-loop, in a closed-loop control, the output of the process is continuously measured by a sensor, whose signal is subtracted from the reference signal to produce the so-called difference signal or error signal.
Staying with the drill example, if you have a reference speed of 1000 RPM, but the drill is only spinning at 900 RPM, the error signal is 100 RPM.
Then, this information is sent back to the decision-making device, the regulator, which knows that the motor needs more voltage to reach the desired 1000 RPM speed. The error signal is, therefore, the input to the regulator, which is needed to produce the input signal to the actuator, and we also need the reference signal at the regulator's input. If you look at our block diagram, it's obvious that a closed loop is formed here as opposed to the previous case. That is why it is called closed loop control. The essential advantage over control is that the controller knows the effect of the intervention. Using this knowledge, the controller runs an algorithm so that in response to a change in the reference signal or a disturbance from the environment, the intervention reduces the error signal. So if I hold down the drill chuck, which is a disturbance, the regulator will increase the voltage so that the speed doesn't drop. This, of course, would only be if we made a drill with a regulator. Many times, the correction is proportional to the error signal, which is put into the intervention signal. If the drill is spinning not just 100, but let's say 200 RPM slower than it should, then twice as much voltage will be generated as a correction. So, the controller's job is to make the controlled characteristic equal to the value of the reference signal. The block diagram of the closed-loop control system can be complemented with the subtractor, amplifier, and disturbance blocks. For simplicity, not all of these are shown in the figure.
Could you give us an example from an industry where regulation is essential?
Of course, there are many industrial examples. Control engineering is perhaps the most important part of industrial control, as most of the industrial systems encompass several types of control systems. For instance, in a nuclear power plant, we cannot use a simple open-loop control system, considering that if the actuator does make sure that the graphite rods that slow down the reaction are in the right position, then we might notice this error too late. Therefore, we need a closed-loop control system that automatically adjusts the process output. For example, it controls the output of the process with the highest possible accuracy to 10 megawatts according to the reference, which is 10 megawatts.
So we have clarified what the two types of control systems are. One is control and the other is regulation. In control, there is no feedback, whereas in regulation, there is feedback. i.e., in regulation, the controlling device has information about what is happening to the control process and can correct the effect of unexpected external intervention or inaccuracies.
Exactly, and thanks for the excellent summary. We do not intend to put any more theoretical knowledge into this video. However, we can see that you have a scooter. To operate it, you will definitely need to control it, and if I'm guessing correctly, it will probably rely on microcontrollers. Could you tell us a little bit about why you brought this device and what role control plays here?
That's right. Today I came by an electric scooter, it's on the right next to us. I'm sure you've seen a lot of these on the street, but you probably didn't think about the fact that there's a microcontroller working on this one, on probably several microcontrollers, but usually they run a control software. What these scooters have in common is that most of them include a cruise control function. This cruise control function is used to make sure that the scooter always keeps the speed you set. Otherwise, this is also used in cars. Next time you happen to be driving, give it a try. In practice, this means that if I'm on a long straight road with this scooter, I can turn on the cruise control with the switch on the handlebar and say I want to go at 20 km an hour. In other words, I set the reference speed to 20 km an hour.
Can we stop here for a moment? You said you wanted to do 20 km an hour, for example. You also talked about reference signal conditioning, which means I can't set any speed, right?
That's right. The top speed of this scooter, I think it's around 25 km an hour. So obviously it's not going to go as fast as a car. So when it's set up, the reference signal conditioning is actually clearly done. From this point on, the process is similar to the nuclear power plant example. Based on the error signal, the controller calculates how the intervention signal, i.e. the motor voltage, needs to be changed to achieve the required speed, i.e. the required wheel speed, and the change then is made via the actuator. The feedback here is provided by the speed sensor in the wheel. So it doesn't matter if the road is uphill or downhill, or even if a friend is climbing up behind you, the scooter will always go at the set speed and the throttle will operate automatically. Anyway, it's interesting to note that PI or PD or PID controllers are often used to such applications, which will be discussed in the Crystal Clear Electronics 2 videos.
Yes, and you can also read a bit about it in this chapter.
That's true.
Well, thank you very much for bringing in this device. Thank you for this little summary and the example of its application. Keep using the scooter in good health. It was good to see that what we are learning is all very much theory, but how many places in everyday life we can encounter these things?
Yes, they are everywhere. In our upcoming video, we'll start with a summary of what we've learned about control, and then we'll get started on building a controller with a microcontroller. We will control the speed of a tiny fan. Now, thank you for attention, and goodbye.
Bye bye!